Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good morning, or late morning to y'all. My name is Mike Sinclair. I'm director of the small but active hardware devices group in Microsoft Hardware. And today we're bringing you a series of lectures from the manufacturer of our laser cutter, laser engraver, Universal Laser Inc. They hole up in Scottsdale, Arizona. Well, I understand it's nice and cool. I know it's not. It's not the heat; it's the humidity, right? So, at the risk of repeat, those of you who are watching all these seminars, we got our laser cutter, which is a Universal Laser Inc. M300, about 8 or 9 years ago, and I don't think there have been many days that laser cutter hasn't been used in our lab, and we pretty much make it available to anybody at Microsoft, not just Microsoft Research, and it's used honestly more than a screwdriver in the lab. It's a very universal tool. We have a 3-axis CNC machine. It got used some before the laser cutter came around, but the problem is you spend 60 to 80% of your time fixturing, just how to clamp the material, your workpiece you want milled, drilled, or otherwise processed, and making sure the CNC knows where those clamps are and doesn't mill through the clamps. And the laser cutter eliminates that. So from concept to finished product can be just a couple of minutes, literally. It's amazing. Wish I had it when I was growing up. I would have made my own toys. Anyway, it gives me great pleasure to present Joe Hillman from Universal Laser Inc. To present the third in the lecture series entitled Laser Interaction with Materials and Laser Application. And Joe is the manager of the Advanced Material Processing at Universal Laser Inc. and did a stint at MIT in material science. Joe?
Thanks, Mike. Thanks, Mike. So in this third section, we'll talk a little bit about what the laser beam does when it hits particular materials, how those materials interact physically with the laser beam, and how to take advantage of those interactions to create some interesting applications. So we want to make this as useful as we can. So as we go through this, if you've got any questions or comments, please let me know, and we want to encourage as much discussion as we can. So the key elements of the laser interaction with material are really heat transfer and mass transfer related. So we've got radiative heat transfer, of course, with the laser beam itself, essentially radiating to the workpiece. We've got conductive heat transfer. Once the material is hot, we're going to conduct heat through that material, and we want to manage how we conduct that heat. And then as the material is heating up, of course, it's undergoing melting, it's undergoing some vaporization and some chemical reaction, all of which result in effluent being ejected from the surface. So the key, really, the three keys to getting the results that you're looking for on your workpiece have to do with managing these three elements: the heat transfer to the workpiece, heat transfer through the workpiece, and the ejection of the effluent from the surface of the workpiece. So let's talk about the heat-affected zone first. As the laser beam impinges on the surface, it's going to, by one of various mechanisms, it's going to cut into the surface and eject some material. But as it does that, it's going to create this, what I drew in pink here, this sort of heat-affected zone. And various things can happen in that heat-affected zone, and we'll go into some of the mechanisms. But the thing we want to control is the things we want to control are melting and charring predominantly. Materials that melt, sometimes with acrylic you want a nice shiny edge, so you want some degree of melting so you can get that nice shiny edge again. But you don't want too much melting. You don't want the berm to form on the edge, and you certainly don't want heat to build up to the point where you get a fire started, and that's just going to cause a big mess and maybe some danger. Some of the degradation mechanisms that lead to the formation of this cut are chemical reaction mechanisms that lead to the buildup of carbon along the surface, which results in char that you usually don't want. So you want to minimize the formation of char as that reaction proceeds. We also want to control the effluent coming off the surface, and the effluent that results from the cutting process is the result of several factors. The material itself is going to control what is liberated as it's cut. The degree of melting, thermoplastic materials, branched polymers, typically those materials will melt as they heat up. They soften and melt, and if they melt sufficiently, you literally blow the melt off the surface of the material and get some penetration that way. Thermosetting polymers are cross-linked, and they typically won't melt. They need to undergo some sort of a chemical reaction, either a pyrolysis or a combustion reaction, in order to create a cut or an etched surface.
I'm not a materials guy. So, like, is standard acrylic a thermoplastic or thermosetting?
Acrylic would be a thermoplastic. Most of the materials that you'll work with, polypropylene is a thermoplastic, polycarbonate's a thermoplastic. Generally, the way you can tell, I mean, just as a rule of thumb, if it's kind of glassy, and if you drop it on the ground and it shatters, it's probably a thermosetting material like Bakelite. It's one of the early thermosetting materials. Thermoplastic materials tend to have some elastic characteristic to them. The decomposition mechanism we'll go into some detail, because that's really one of the keys that you can control. But with the amount of laser power you put in and the amount of air, and either adding air to the reacting surface or starving the surface for air can impact that mechanism. And then, of course, something we've got direct control over is the laser power density. The laser power itself, the duty cycle, how long a given pulse stays on, the repetition rate, or how many pulses per linear inch we're imparting to the material, and the carriage speed. If all else is constant and we're moving very slowly, then we're putting a very high power per unit length into the workpiece, and if we run fast, we're putting less power density into that surface. So acrylic, I think, is one of the most useful materials for general construction, and certainly very amenable to laser processing. And one of the reasons that it is so amenable is the way it reacts with the laser beam. Acrylic is polymethyl methacrylate, so this is the methacrylate unit, and this convention, these brackets here with the N, means that methacrylate unit is repeating over space 10,000, 20,000, 25,000 times for the very high molecular weight acrylics. When you heat this acrylic up by applying a laser beam, it goes through a depolymerization mechanism, which just means it started out as methacrylate and goes through a reaction process to build up these long chains. When it decomposes, it's just breaking back down into this methacrylate monomer, which is up here, which is a liquid at standard temperature and pressure. Now that methacrylate monomer, it's still susceptible to laser power, and it can break down further to carbon monoxide, carbon dioxide, hydrogen, water, which of course are all volatile. But in terms of mass transport, the largest volume of effluent is going to be this methacrylate monomer. So what this means for practical purposes is you're going to have a very clean cut. This is a colorless liquid that's going to be evaporated from the surface, and as long as you've got a good exhaust flow, it's going to be carried out the exhaust stream. You need to be very careful with the exhaust stream, because if it recondenses, it's going to solidify on the surface, and you're going to get a very hazy surface. And we were talking a little earlier during the break about some of the things that you can do to control that. One of the common things to do if you're going to etch into the surface and then cut it later would be to remove the protective liner, do your engraving, because it's hard to control your engraving if you're engraving through the liner as well as into the material. But then after you've done the engraving, you want to put some sort of a liner in the form of transfer tape, or sort of a virtual liner that we tend to use is just dish soap. You can cover the surface with dish soap, so that if material does fall back, it's falling onto that liner, and if it's a liner like transfer tape, you just pull it off. If it's dish soap, you just wash it off. So you want to have the liner removed to do the engraving, so you can get your fine detail engraved into the surface. But then for the cutting step, you've got to have the liner back in place, because you're going to liberate a lot of this methyl methacrylate with the high energy of the cutting process. So you need to have something that methyl methacrylate is going to fall back out on. But generally speaking, polymers that go through a depolymerization mechanism when they decompose give you a very clean reaction, and they leave you with a very clean cut edge. Certainly you can get char. If you have a fire, you're going to have char, but generally speaking, the laser process is a much higher power density process, so it's going to liberate this methyl methacrylate and leave you with a clean edge. And if it's useful to folks, I can kind of create a list of useful polymers and what their typical decomposition mechanism is. Backbone scission is another decomposition mechanism, and it's kind of a special case of depolymerization. Actually, the other way around. Depolymerization is a special case of backbone scission. So backbone scission, we've got this long polypropylene molecule in this case. So the repeating group here is the propylene monomer. It repeats in space again, 10, 20, 30,000 times. But when you apply energy to polypropylene, it's not going to break right here and right here and liberate a whole bunch of propylenes. It's going to break randomly and yield lots of chains like this 2,4-dimethyl 1,1-heptene. We've got an organic chemist on our staff, so he drew all this stuff up for me. Pentane is volatile. Methylpentene is also volatile. Of course, we're always going to get the carbon monoxide, carbon dioxide, hydrogen, water coming off. Now, these are the volatile components that are, if you've got a perfect decomposition, even through backbone scission, and you only yield these are volatile and they're going to go away. But in the heat-affected zone, you're going to have complexes of these chains, some of which aren't going to be volatile. They're going to have more heat applied to them because they're in the heat-affected zone. They can fold back on themselves and recombine. They can create double bonds. They can cross-link to other similar polymers. And the result, in general, when this is happening, under the influence of heat and generally not enough oxygen for complete combustion, is you concentrate carbon right along that cut edge. And that concentration of carbon is what we commonly refer to as charring. For a polymer like polypropylene, it's controllable. If you put sufficient power density into the surface and you control it so you're not building up too much heat. In other words, you want to hit it with a high power pulse so you can get through the material, but you don't want the pulses to be spaced too closely together. That's how you avoid building up heat in the in the along the edge, you can avoid this edge charring if you've got the sort of backbone scission mechanism. So it's not a guaranteed clean surface like you'd have with depolymerization, but it's a very controllable decomposition mechanism.
Vector cutting and vector etching of acrylic a lot, and if I take that material and then before I started using transfer tape, I used to try to wipe it with an alcohol rub, and often I'll get cracking on the surface right at the etched point, at the heat-affected zone. What's going on chemically there that's causing that?
The alcohol is leaching the polymerizer out of the acrylic, and it's just making it very, very brittle. It's essentially drying it out.
Just the alcohol.
So is that, why am I seeing that only at the heat-affected zone? Has that already been weakened in some way? And then that's where
It's been changed chemically. Yeah, it's breaking down. So the application of the heat is making it more susceptible to the alcohol, definitely. But acrylic is very prone to moisture uptake, for example, and it does the same thing with the alcohol. It can take up alcohol, and the alcohol, as it evaporates, it's carrying away the polymerizer out of the plastic matrix.
Yeah, I've seen it craze acrylic even with other applications too, not even laser alcohol.
Especially if you've got an extruded acrylic. Extruded acrylics are much lower molecular weight because they have to go through an extruder. And those are extremely susceptible to moisture or to this cracking and crazing mechanism.
So we should use cast instead of extruded for that?
Yeah, cast is the benefit of extruded is it tends to have a much more uniform cross-sectional thickness, but the problem is it's just not as high density a plastic. So if you're going to if you're making something that's going to be submerged, for example, if you're doing a fish tank part or something, definitely want to use cast acrylic.
How about the berm size? How does that vary between cast and extruded?
Generally speaking, the cast acrylic you're going to be able to control the berm size better because you're going to have less of a tendency to melt rather. Also, you tend to get a much more discernible high contrast mark if you want to mark in cast acrylic as opposed to extruded acrylic. Extruded acrylic, you kind of get a melt and a reflow across the surface. On the other hand, the extruded acrylic, you can get a nice, beautiful, shiny edge if it's the appearance of the edge that you like. It won't be as square as the cast acrylic edge.
Is the density of cast greater? I thought you said the density of cast was actually greater than the density of extruded.
Well, literally the molecular weight is definitely higher. I'm implying that the density is different just by certainly by observation. The extruded acrylic will take up moisture much more readily than the cast acrylic. I don't know if the literal, if measured as grams per cubic centimeter, if it's really a higher density. It's always a higher molecular weight.
Is it stronger?
It's
In certain directions.
Exactly. Yeah. It's more brittle. I think it has a higher tensile strength, but it's also more brittle.
How can you reduce charring in cutting polycarbonate?
Oh, you must have looked at the presentation. Okay, so polycarbonate's a fairly complex molecule. It's got a cyclic component to it, and under the application of heat, these cyclic units, you can get more cyclization. It's a hard thing to say. You get effluent components that are cyclized, but again, what I'm showing here are the volatile effluent components. And as you're burning through the material, you're creating longer chains of these, which again have a tendency to fold back on each other, undergo recombination, you create lots of double bonded carbons, and create more cyclic groups. It's much more difficult to control char with something like polycarbonate. Basically, what you want to do is the same kind of thing that we wanted to do to control the backbone scission mechanism is hit it with a very high pulse energy and then spread the pulses out so you're vaporizing material in the path. You want to create these volatile phenol and bisphenol groups and not create the longer chains that are going to cyclize and recombine and undergo pyrolysis. Pyrolysis is basically combustion in the absence of oxygen, so you're naturally going to get a high carbon content. So one thing that people do, which we unfortunately can't do with our system, is use a Q-switched laser that gives you a much higher peak power. You can have peak powers that are 1,000 times higher than the average power of the laser. Yeah, at least 100 times higher than the average power of laser. So you can get a very good peak that vaporizes the polycarbonate and doesn't leave charring. We're actually doing some work. I'll let you know how it turns out. We're trying to just maximize the power of the laser and at least maybe use the HPDFO to focus the beam better and at least get through some thin polycarbonate without any charring. Probably be doing that within the next couple weeks.
The other thing I've seen with polycarbonate is a lot bigger berm. Is that also addressed by the higher power, lower pulse rate approach?
It's addressed by it, but there's only so far we can go with the CO2 rate or CO2 laser without Q-switch capability. But it's due to the same mechanism, the fact that while you're creating these volatile components, you're also necessarily creating longer versions of them that just aren't going to go away.
So what's the best strategy with your CO2 laser to cut polycarbonate? For example, one could do multiple passes and multiple cuts at lower powers, or what is the optimal strategy for minimizing?
Yeah, I don't like doing multiple cuts. I would prefer to use the highest power you can, and then turn back either the pulses per inch or the percent power, and try to get the best cut you can. But the high peak power is really the key. So probably what you want to do is minimize the number of pulses per inch, and that's part of the experiment that we're doing, actually, seeing which one works better. But it would be those would be the two control points: pulses per inch and percent power. But definitely the highest laser power and the smallest spot size you can get would be the best way. I've seen people cut successfully with multiple passes, but you're not literally cutting halfway down and then cutting the next half, because you got beam interference with the edges, so you tend to char the edge of the first cut as you're trying to get through the second time. Okay. So those sorts of reactions are the most difficult to manage, and again we're kind of in the process of putting together a list of which molecules undergo which reaction mechanisms, with two driving points. The biggest driving point is we want to know what's in the effluent so we can design a better exhaust cart, one that can guarantee that we're catching the components that are coming off of the surface, and we want to be able to inform people, if they're cutting novel materials, what safety precautions to take and what to be careful of. But the other reason is just so we can understand what's being left on the edges of the cut and how to control them better. So as we develop that, we'll make sure we get that information to Mike and the rest of the folks here, so we can we want to share it with you as we develop it. Okay, we'll switch gears from cutting to marking a little bit. Talking about marking polymers first. Now, probably what you see most of the time when you want to put a mark in a polymer with a CO2 laser is you're doing it by ablation. You're cutting through the polymer. It's the same mechanism. You just don't cut all the way through. If you get about 10 thousandths into the surface, you can create a pretty visible mark. These marks, sorry, you probably can't see it very well from there, but these marks aren't any more than 5 or 10 thousandths deep, and at least at my distance, they're pretty visible. Other mechanisms, though, are foaming. I hope you can see that. If you apply power very gently and spread the beam out across the surface and begin melting the surface of the polymer and just begin volatilizing that melt, so essentially you're just starting to boil what's melted there, and then you move the laser to the next spot quickly enough, so you're creating the bubbles and then freezing them in place. You can get a mark that's a foaming mark, and these are useful. It's a bit hard to control. Only certain polymers really lend themselves to foaming. Nylon is one of them. But if you've got a particular marking application where you just can't tolerate any depth, if something that you don't want to catch a fluid or something like that, foaming is a good mechanism. Bleaching is a good mechanism. So these would be dyed polymers that have one natural color, but they're dyed a different color, and a laser can bleach that dye mechanism. Now, typically, these dye mechanisms respond better to a YAG or a fiber laser frequency at about 1 micron than they do to CO2. So you'll typically see bleaching done with a 1 micron laser rather than a 10 micron laser. And finally, carbonization. This is ABS is a good example of a polymer that you can mark with carbonization. You carbonize the surface and you just get a black mark on the white ABS. So this is a case where you're trying to maximize the amount of char on the surface. You want to take it through that decomposition mechanism, but without volatilizing any of the components.
So how do you achieve that with the lasers? Is that just really low power or low speed? Or?
Appropriate power and appropriate speed, right? You want to, because it depends on the polymer itself. Certainly lower power than if you were going to cut through it. Lower power density than if you were going to cut through it. Yeah, and you generally want to spread the beam out, so defocusing or using a longer focal distance, longer focal distance lens would be appropriate.
What about cutting ABS? It seems like that just sucks.
ABS, yeah, tends to melt. It's a hard one to cut with a CO2 laser. The best strategy, again, like with polycarbonate, is to maximize your peak power and minimize the number of peaks, so you're not building up heat. It's possible to cut through it. You can cut through it. You tend to have a big heat-affected zone, and it catches fire pretty easily.
Seems like the thinner materials obviously are not as bad, but
yeah, thinner materials are better because you can get through them easier, but also there's not a lot of cross-sectional area to support heat transfer into the bulk of the material. We can mark metals. I showed this sort of generally for marking metals. Certainly metals can be marked with ablation. Again, this is something that's not done very readily with a CO2 laser. For ferric metals, iron or steel, we can get some ablation. We can probably get a couple thousandths into a piece of steel. But generally, marking by ablation is done with a shorter wavelength, like a fiber laser, a YAG laser, or a very high power 1,000 watt or better CO2 laser. Surface oxidation. This is the mechanism that we use to mark titanium or steel or stainless steel with the high power density focusing optics. If you've got a YAG or a fiber laser, you can carry this mechanism pretty far, and you can get interesting colors. You can get reds and blues out of stainless steel surfaces. Bleaching is done typically with anodized aluminum. So if you've got a piece of anodized aluminum that's blue or red, so it's just a white anodization, but anodization is very porous. So that anodization is dyed. The cracks in the anodization suck up the dye, and then what the CO2 laser is doing is just bleaching that dye out of the surface. And then the fourth mechanism is marking compounds. So this was developed specifically for CO2 lasers, for materials that couldn't be marked, like glasses and metals. It's a ceramic slurry that's either sprayed onto the surface, or it can be painted onto the surface, or there are actually tapes that you can apply the tape to the surface. Then you hit that material with the laser. The laser power sinters the ceramic elements of the slurry together and sinters them to the surface, and you've got a fairly indelible mark then on the surface that has a little bit of height to it, maybe a thousandth of an inch above the surface. So these are available from a couple companies. Thermark is one, and Cermark, C-E-R-M-A-R-K, is the other. And then glass is a fairly unique case. So we can't ablate glass away, at least with a CO2 laser. We heat the glass locally, which causes micro cracks in the surface. It can be a very nice effect. It makes it look very white. It scatters light. The other mechanism for marking glass would be a marking compound, like Cermark or Thermark. There's special varieties of Cermark and Thermark that are made to bond better to glass than to metal.
Do you think you could pulse fast enough that you minimize any kind of melting and just promote the cracking and diffraction?
I've seen that effect, and maybe you can manipulate it with by the way you pulse the system. We can certainly work on that. Where I notice the effect is if you look at different kinds of glasses. If you look at soda lime glass, we don't see any melting at all. It tends to crack and sometimes pop little pieces of the glass out of the surface. Pyrex melts and cracks. And if you look at fused silica the surface just tends to melt.
So is it possible to laser cut glass, any of the kinds of glass?
It's possible to laser cut glass. There's a company, Jim knows the name. There's a company that makes a system. I think it's CO2 laser based. It's a Swiss company. I'm trying to think of the name, it'll come to me. But basically they're using the laser to heat the glass, and then they've got a liquid nitrogen source on board that blasts liquid nitrogen right behind the heated portion of the glass, and that just forces a crack tip along the glass. And they can actually get very, very intricate patterns of very nicely cut glass.
I've heard of someone with one of these systems cutting through a microscope slide. It took a long time, but it was 5 days.
I see.
It's slow, yeah.
But using this sort of system to do the micro cracking, to do etching, just on normal plate glass or so forth works well?
I haven't had any success just using our system directly to cut glass.
I meant to do the marking of glass, to do this micro cracking.
Yes.
That works well on this.
It works quite well, yeah. That works quite well. Mm-hmm.
Could you use that to promote cracking so you could break it on the line of the crack?
Fundamentally, I think you can. I haven't had much luck with it because the cracks run off in different directions, so it doesn't tend to. I'm used to working with quartzware or SEM samples where you can just make a very fine mark with a diamond scribe, and a silicon wafer will crack very nicely. The cracks just go off in different directions. someone more talented than me might be able to do it, but I haven't had much success with it.
So can you do the opposite, on the glasses that melted, maybe on plastics? If you have, kind of a frosted surface that you've roughed up a little bit, can you selectively remelt to get a nice smooth area for marking? That you use the smoothness, basically as the mark.
Sandblast it first and
Yeah.
then smooth it.
Yeah. I don't think so. And if it were fused, and this is just by observation, if it were fused silica, I've seen a melting effect, but on standard, normal soda lime glass, I think it's just going to make it more cracked, and it's going to give it more of a sandblasted appearance if you hit it with the laser again.
At all, you're just getting the cracking.
Yeah.
So the marking compound, just out of curiosity, do they make stuff that you said about 1/1000 of an inch? What if you wanted something that was perceptible? You wanted a bump on your braille. I was thinking braille.
Yeah, you can definitely make it thicker.
So they have these marking compounds that will.
The brush-on stuff is naturally thicker. You just can't get a thin layer of it, so that'll leave a taller mark. The tape tends to leave a taller mark. The most uniform mark we can get, we tend to use the spray on. It's just a spray can, because that's the most uniform application, but it leaves the thinnest mark. You can certainly build it up layer by layer as well. Yeah, that's an interesting idea. You can definitely make it thicker. Usually we're looking for something more uniform and less thick, so
There's always a little stick-on tag.
Yeah.
It's always stuck on, and because it's been bumped out. And if I wanted to etch something onto a metal plate or a glass, or not glass, but
Plastic.
it's definitely possible.
it's like it looks more finished, professional, without sticking the braille tag on it.
Okay. I put together here a general list. This is page 1 of the list of what you can do with various materials. We've got maybe a bit of a esoteric category on the top here. These are generally thin film materials that are laminated together, foams and adhesives. But for those materials, you can generally both cut and mark them. The usual application is to cut them. For example, inside of a cell phone, you'll have various thermal conductors and RF isolation materials that would be cut to a certain size and pattern to pop into the cell phone. But sometimes people want to mark a part number on them or a serial number. Fabrics, similar, we can cut and mark. Glass, I don't have them listed as something we can cut because you can cut them, but not very predictably, so it's not very useful. Metals, extremely thin iron, steel, and stainless steel, like 1 or 2 thousandths foil we can get through in certain cases where we've got, one that's typically done in your lab is aluminized mylar. You can get through that if you use the laser to heat the mylar, and then the mylar in turn heats the aluminum. So there are special cases where you can cut through very thin metals, but I kind of listed cutting with a CO2 laser of the power that we have available as a no. But we can mark all those metals though, either directly or with the laser marking compound.
One more back. So one of the things that we do in hardware, we make a lot of keyboards and stuff, which are the Mylar switch-based things. So we certainly tried to use the laser to do membrane switch spacers. And one of the problems that we continually run into is that the edge develops a little bit of a lip. And so I've been looking for a good way to avoid that. So we've actually, for our testing, to do real thin ones, that we use paper rather than the thin Mylars and stuff, because it doesn't lip up the same way.
Okay.
But is there a good way to control that lip to get it small so it doesn't, because generally with the membrane switches, you're making a hole and the distance is absolutely critical.
Mm-hmm.
when you get that fat lip, typically like on a 2 mil sort of thing, we'll have a 5 mil lip.
Okay, yeah, that doesn't work very well. Typically, the answer is high peak power and fewer peaks. What we'd probably want to do is just, work with you directly and get either have you specify the material that you're using or send us a piece of it, and we can work, side by side with you to optimize the process. And that's a general statement. We've had a lot of discussions about glass and acrylic and membrane switch spacers, but I'll make sure that everyone has our contact information. If there's a special application you want to look into or something you're having trouble with like that, we'd love to have your material and your specification, and we'll just we'll do our best to optimize the laser process for that material and get the process parameters into your hands. It helps us, we're helping you, but it helps us to stay abreast of what the current applications are.
That might have the answer.
No, I don't have an answer, but I found a way of making a chamfered cut on the top, and that might help.
Oh.
So, especially with the new laser that you have programmable Z height, you do a cut, then you lower it, say an inch, and do about a quarter power cut. And it removes those berms,
Yes.
But it'll round the edge. I don't know if that's...
Yeah, that may or may not be okay.
But that might remove the berm.
Yeah, I was wondering if there was something like you could sandwich it in between, if that would help, or that you create a sandwich so that the material that you're cutting, doesn't,
Oh, so you cut
Yeah, I think so.
Yeah.
Something like the transfer tape. You mean something physical, or?
Yeah. I know. So one of our vendors that does this, they use the transfer tape, and it didn't help that much.
Mm-hmm.
So
There are various kinds of liners, different materials. Polyethylene, craft paper. Different. Usually the transfer tape is craft paper based. But the idea is to keep the laser from kind of bleeding over to the edge and melting it, kind of shadowing it from the shadowing the part from the laser. We'd be happy to work on that.
Okay.
We're doing a lot of work in this space right now, so the more we can learn, the better off we are, and the more we can help you. Okay. Polymers, of course, are the most versatile material. CO2 just the polymers are very susceptible to CO2, and I've got a long list of polymers here that we've worked with, and this isn't even an exhaustive list. I think our materials database has well over 100 different polymers in it, 130 some odd polymers that we've worked with at some level. And even natural materials, leather, paper, marble, granite we can mark. I wanted to go into a little bit of depth on acrylic just because it's useful. And what I'll do is kind of use acrylic as a vehicle to show you the kind of characterization that we do in our lab for a given material. And then we'll go through a couple quicker examples after that. But typically, if we get a new material in, and acrylic's obviously one we've got a lot of experience with, but if we get a new material in, we want to understand how it reacts across the spectrum of laser processing, how it reacts to 10-watt lasers, 30-watt lasers, 50-watt, 100-watt, 150. So we literally test them with all those laser powers, and we test them, test various thicknesses. We usually get at least 3 thicknesses from the thinnest available to the thickest available, something in between, if possible 2 or 3 things in between. Because if you're cutting through 40 millimeter acrylic, you need a different power density than if you're cutting through quarter-inch acrylic. So we'll characterize the maximum cut thickness versus laser power, and of course as the laser power goes up, you can cut through thicker and thicker materials. We'll try to characterize how fast you can cut through a given material, how fast in terms of inches per second. So obviously the shape is here, but this serves as a good reference document. If you've got half-inch acrylic, you've got to set it at about 0.1% speed if you're going to cut through it completely, and then you can fine-tune from there.
When I'm trying to guess the pulses per inch and the power, I look at the table in the manual, which has got a couple of points, but then I kind of have to guess from there. Do you make this, detailed data available for recommended settings? Or?
Yeah, we'll put a white paper together for each material. So any material that you want, if we've got it characterized, we'll send you just a 2 or 3 page white paper.
Yeah, I'd love to just have a table that we could tape up next to the laser cutter that just had the graphs for each, thickness and each type of material and what settings to use to cut through it.
In the current system, in the new system, that table is all electronic in the form of a materials database.
Oh, okay.
And I'll right at the end here, I'll show you a quick little video that shows how just a 1-minute video that shows how the materials database works. But basically, you hit from our table, it basically, oh gosh, operates like the table. So if you're cutting acrylic, in column 1 you select polymer, it'll bring up all the polymers, then you select wherever acrylic is, cell cast acrylic, hit that, you'll enter your thickness, and it sets PPI, it sets percent power optimally for that material. So it's the same kind of thing for marking. So we'll characterize the marking performance, but then this information all goes into the materials database. So a user who wants to manipulate the controls manually can, but at least you've got a starting point in the materials database. And for a more a manufacturing environment where the engineer wants to set the settings and just have someone there running parts, the operator can just select the material and hit go, and have the proper settings automatically set for cutting or marking the material. Here's just a sample. This is a piece of acrylic. It's got a black backing so you can see it. But it's marked here. This is a raster mark. More raster marking going all the way down to 2-point text. This is a raster mark and a vector mark where we just kind of trace the outline of the word mark. We cut out the word cut here, and here's the part that was cut out. But all these are based on the materials database settings that are a result of that characterization that we went through in the lab. This is a little microreactor that we made, again using materials database settings. We had this particular design where red are, in this case, red are some vector lines marked into the piece. We had to cut the whole piece out, cut some through holes, and then raster these red and yellow cavities. And I don't know exactly how this works, but presumably some fluid is placed here, and capillary action draws it up into this mixing zone, and it mixes with other fluids in these other cavities. It's interesting though, in that it kind of taught us how to control channel depths and widths. So in this case, it's a little hard to read here because all we've got is 230 power microscopes. This is the best magnification we can get in our lab, but it's about 100. It's 97 microns by 90 microns deep, and it was very controllable. We did a characterization over several powers, and as we increased the laser power, we were able to pretty predictably control both the depth from about 20 microns deep up to 130 microns, and control the width from about 50 to about 110 micron width for just a vector cut across the surface of a piece of acrylic. For the raster cavities, I'll show you a similar graph in a second. We were able to control the average depth and average width pretty well, but if you look at the microsurface of the cavity, it's pretty rough. And actually, typically, if people are going to do a microreactor, what they're going to do is have a quartz or a stainless steel backing plate. They'll deposit the polymer on top of that, and then when they raster, they can just overdo it and raster all the way down to the quartz and have a nice flat bottom. But we wanted to see how good we could do with going into bulk acrylic. And the behavior, actually, for as bad as that bottom surface looked, the behavior is pretty linear. As power increases, we were able to control the depth, the average depth, pretty accurately. Stainless steel marking. I guess I should walk through this table. This is a typical table we'll create for an example process if we want to have a single point in the whole variable space. So we've got a piece of stainless steel. We ran it on a 6150D. D is a dual laser system with high power density focusing optics. We've got a 30-watt laser. And then here's all the process conditions. 100% power, 3% speed, 500 pulses per inch, with an image density of 5, which corresponds to a line-to-line, not spacing, pitch, line-to-line pitch of 500, 500 per inch.
It must take ever.
It's slow. Direct marking with the HPDFO is slow. It's a more indelible mark than using the marking compound, but it's slow. A piece like this probably takes, you can't tell what the size is there. This is a business card size. Like a 3.5 by 2 by 3.5, I think, is business card. It probably takes about 5 minutes to mark. This piece really highlights the fineness of engraving we can get. This is 2-point text. You can see a ballpoint pen right here. It's 2-point text. You can't read it with the naked eye, but with a 10x eye loop, you can read it. It's legible text. So we get some really fine marks with the HPDFO. Aluminum, if it's anodized aluminum, as we mentioned before, and the anodization has a dye in it, we can bleach that dye. In this case, what we've got is a mark that is done with Thermark. It's the spray-on material that's sintered onto the surface. But again, we've characterized the whole process, and we make our characterizations of the process available to any of our customers, either on paper or through the materials database. And of course, the database is really the preferred mechanism because it's right there.
So arc and so forth, you spray it on, do the sintering, and then just wipe off the excess?
I'll wash it off. It's water soluble. Glass marking. So the glass marking is even though it's just a series of little micro cracks on the surface, it scatters light pretty well and leaves a nice white-looking mark with a pretty good contrast and pretty fair definition. So here we're at 100% power, again with the 30-watt laser. Speed's substantially faster, 40% speed compared to 3% speed with the stainless steel.
Do you have a black paint on the back of the glass? Is that?
Yeah, this is actually silkscreen black on the back, just to make the marking stand out better. Okay, this is the last one I wanted to show you. We just took an LCD screen apart, and as you know, the LCD screens have various optical materials in them, anti-glare, anti-reflective films on the top, prism films and polarizers on the top and the bottom. We just pulled them all out and tried to cut some interesting patterns into the materials. So we took one of the top films, anti-glare, anti-reflection film that was 10,000ths of an inch thick, cut it with a 50-watt laser, and these are the settings we arrived at as the optimum settings. So just to kind of highlight what we do when we do a full characterization, we put together a little video that shows how the materials database works that I'll bring up for you as kind of a wrap-up, just because, but kind of walk through it. Okay. Well, this is Visio, so we'll make up for it. Okay, so you open your graphic, whatever your graphic is in your selected software. In this case, it's Visio. Okay, so we just chose a kind of complex graphic here. You know, this isn't anything useful, but we wanted to do a pattern that would kind of demonstrate the capabilities of a laser with respect to a rotary cutter or a knife cutter or a die cutter. Things like this shark tooth pattern it's very sharp, and if you tried to cut it with a rotary cutter, you just tear the edges off. These square rectangle patterns have about a 15 thousandths wall between them. So if you tried to cut those with a die, you'd probably pull it apart. So, and that's the reason for this oddball shape. So I'll just run through it from here. So once you've selected the graphic, you just hit print right here. Not used to 2 screens. So you hit print, that sends it to our print driver. So that's where the materials database is. So we select optical films, list of optical films comes up. We select the anti-glare, anti-reflection film. That sends it to our process interface. You hit the start button. Let me go back again. I went a little too fast there. So that sends it to our control panel. Once it's in our control panel, you just hit start. You've already selected the material. I'm sorry, let me go backwards again. I should have stopped it there. So we've selected print from Visio. That sends it to our print driver. So this list of categories comes up: electronic materials, membrane switch materials, laminating adhesives, optical films. The full materials database would have plastics and metals, etc. But if we select optical films, diffusers come up, prism films, reflective polarizer, and then the one we selected here is the anti-glare, anti-reflective film from the front side of the stack. Enter the thickness here, which is 10 thousandths, and then press go down here, or OK rather. That sends it to our control panel. So everything is now downloaded into our control panel. So all the user has to do, there are lots of capabilities to make setting changes if desired, but if we're running right off the materials database, all we have to do is press start. As soon as you press start, the laser starts up. So here's the carriage and of course the XY arm, and we're cutting out our pattern.
What's that material you're using as a vacuum?
It's tape. That's just transfer tape, covering up the open space in the cutting table, so that the vacuum from the exhaust holds down our material. So that's the final material, and we actually did that for all the films that we found, prism film, and I think this was the anti-glare film, and a polarizer film. So it's useful for cutting any of the thin film materials within the display. So that was kind of the highlight. There's a summary slide on the PowerPoint presentation, but I don't know if I want to try to figure out how to get back to that. But hopefully this has been valuable for everybody. The real goal is to try to give you some more insight into laser processing, but also to begin establishing a good relationship, so that as you come up with new applications, you feel free to call us and let us know what you're working on, and we can put our expertise together and help you develop a more optimum laser process for your application. Any other comments? I don't know how tied to time we are, but I'll be happy to stay and answer questions. And
does anybody have any questions or comments or discussion?
I'll ask her.
Good.
thank you.